So in the last session, we had given a brief introduction to the course and also to the topics that we will be considering. Also, what is the basic definition of a discrete time signal? So let us take a quick look at some of the topics and then move forward. We looked at the differences between a continuous time signal and a discrete time signal, why we call some of them as discrete time signals versus a digital signal. Now, to encourage you to get a good understanding of this topic, we'd like you to look at the textbook, Oppenheim and Schaefer, look at sections 2.0 and 2.1. These are topics that we are going to be covering, and also in the reference book, Rawat, section 1.1 to 1.3. And again, if you have any questions or doubts, please email Mr. Tony or myself, and we will be happy to respond. So we are going to dive into the topics for the first week of our study. And we said, this is a picture from the last time. We said that if you look at a continuous time signal, the xa of t is the green signal, which is then periodically sampled at ts, 2ts, 3ts, and so on. And if you represent these values with infinite precision, that would be a discrete time signal. Now, as opposed to if you quantize the samples that you obtain, then you would get a digital signal. So this is where we would like to make some of the differences and clarify. So if you had a continuous time signal xa of t, which you pass through a sampler. So we will call this a block that is converting from continuous time to discrete time. Okay, notice that we are calling it C to D, not as an A to D. So this is the input signal xa of t. This particular sampling device, you have to feed in what is the sampling period, and then output of this will be x of n, the discrete time signal. So this is what is called a continuous to discrete time converter. And if you then pass this through a quantizer, so at this point the discrete time signal is, we can say that it is discrete in time, but it is continuous in amplitude. So let me write down a reference way of notation for this. So C will represent continuous, D will represent discrete, and T will represent time, and A will represent amplitude. Okay, so let me keep this as a box that you can refer to and use this to understand what is the notation that we are introducing. So xa of t, if you were to describe this, this would be continuous in time and continuous in amplitude. Okay. On the other hand, x of n, the discrete time signal, it is discrete in time. So therefore, d and t followed by it is continuous in amplitude. So that means you are representing each of the signals with infinite precision. Then comes the quantizer. This is the place where you would represent each sample by a finite number of bits. It is denoted as q of x of n. Okay, you quantize the signal x of n using a quantization mechanism, which will call it as q, which reduces the number of bits to a finite number of bits. Okay, and this produces for us x n hat of n, and the representation of the signal here, it is discrete in time and discrete in amplitude. Okay. So I hope you are following. We went from the first step, a continuous time signal, which is continuous in time and in amplitude, to a signal x of n, which is discrete in time but continuous in amplitude, and then finally to a signal which is both discrete in time and discrete in amplitude. So if I were to draw a box around this, these two together, the C to D and the quantizer together, this is what will be an A to D converter. So, an A to D converter not only converts a continuous time signal to a discrete time signal, but it also quantizes it to a certain number of bits. Okay, a good way to represent it is by means of a simple table. Let me write that for you. Okay, so if I have a signal xa of t, then I have x of n, I have x hat of n. So, in terms of amplitude, a continuous time signal xa of t is continuous. The discrete time signal is also continuous in amplitude. The quantized signal is discrete in amplitude. In terms of the time axis, the continuous time signal is continuous in time. The discrete time signal is discrete in the time axis, and of course x hat of n is all discrete here as well. So you can remember this in the form of a table, which will be helpful for you to keep in mind. Okay, so when do we call a signal as a discrete time signal? When do we call it as a digital signal? I hope is clear. But as far as our course is concerned, we are going to be primarily talking about discrete time signals. We're not talking about quantization. The effects of quantization can be studied and will be covered towards the end of the lecture of the course, but for the most part, we are going to be looking at it from in the context of a discrete time signal. Let us move on. So, one of the ways in which we get the discrete time signal is through a process known as periodic sampling. And in the last lecture, we said that we can obtain the samples at regular intervals called the sampling period Ts. The sampling frequency will be 1 over Ts. The units of sampling period is hertz, sampling period is seconds, and sampling period frequency is hertz. Now, T is a continuous variable. X of n can be real or complex valued. X of n will also be real or complex valued, but notice the condition that n has to be an integer. Only if n is an integer, this is defined. And we said that the process of obtaining a discrete time signal from a continuous time signal was through a process of sampling, which would be governed by the Nyquist sampling rate. So, the Nyquist sampling rate, we said, enabled us to go from continuous time to discrete time without loss of information. There is one additional qualifier for the use of the Nyquist sampling theorem, and that is the assumption that the signal that we are dealing with is a band limited signal. So, the Nyquist sampling theorem is for band limited signals. For any band limited signal, let me just describe what a band limited signal is. If you looked at the Fourier transform of this signal, then this signal would have a frequency content which is limited to minus f0 to f0, somewhere within, and beyond that region it is 0. So, this would be the response of the signal. Let us say the signal that we are talking about is x. The Fourier transform of the signal. If it is finite in terms of where it is non-zero, then this is a definition of a band limited signal. For any band limited signal, the Nyquist theorem can be applied, and therefore we have a representation of the continuous time signal as a discrete time signal without any loss of information. So, that is an important aspect that we want to keep in mind. And notice that there is also a class of signals which are inherently discrete time. So, either you can get it from a continuous time signal which is band limited through a process of sampling, or a signal that is inherently discrete. So, okay, so that is broadly for us. Now, I wanted to just refresh your memory and also to give as an additional example this particular calculation. This is a continuous time speech signal, the signal A. We are going to be sampling it at 8 kilohertz. We said that means it's 8,000 samples per second. And if you quantize each of the samples to 8 bits, then what you will get is the digital signal. So, this is x hat of n. Okay, the continuous time signal, this is xa of n, xa of t. Okay, so maybe we just call this as xa of t, this as x of n, and then when you quantize it, it will become x hat of n. X hat of n has 8,000 samples per second. Each sample is represented with 8 bits. So effectively what you will get is 64,000 bits per second. So this is how a digital signal is represented in terms of a certain number of bits, and this is very helpful and useful for us to keep in mind. Okay, and then we said that once you have a discrete time signal, you represent it as a sequence of numbers, x of 0, x of 1, x of 2 and so on, x of minus 1, and when you write it as a sequence of numbers, you will always indicate where the 0 point lies. So, for example, if you had a signal which consists of 1, 2, 3, 4, 5, you need to know where the 0 axis is. So, this corresponds to the value x of 0. The next number will be x of 1 and the next number will be x of 2. And similarly, on the other side, you will get x of minus 1 and minus 2. So, that is the notation that we will follow, and also notice that always the argument of x of the function will always be square brackets. That is the convention that we follow for a discrete time signal. So, this will be x of minus 1 and this sample will be x of minus 2. And we are able to derive that because from the position of the arrow. So, this is the broad definition of a discrete time signal, and now we have the basic notation for us to quickly dive into the various discrete time signals and the continuous time signals.